right, hello everybody. Welcome to part 2 of the notes on electron configurations. I just want to remind you really quickly what we did in part 1 so that you're ready to transition to part 2. So I'm going to back up on our presentation. These were the answers that we gave for the electron configurations for different elements. So you had to look at nitrogen, chlorine, and niobium, and you had to try to draw them out. I'm sure you can imagine that trying to draw out the electron configuration box charts, what I refer to it, the orbital charts, is super time consuming, and that's not something that scientists are really going to do. So scientists are always about being more efficient. So that's what we're going to learn in this second half of the notes. Now you've seen how the electrons get assigned based on the box chart. Now we're going to try to write it more efficiently, and we'll do the longhand version first, and then we'll get into a shorthand version that'll be a lot easier to write. So let's start with the longhand version. So it says, instead of drawing all the boxes and arrows, which for beginners, you need to draw the boxes and the arrows so that you know what's going where. You'll get the hang of it, and then you won't have to do that anymore. The configurations are written just with the level and the number of electrons contained in that level. So let me give you an example. Let's say we have an element. Oops, I was going to have my periodic table handy so I could look at it. Here's my handy dandy periodic table. You come teacher can't be without it. Let's say we were going to look at lithium. Lithium has 3 electrons. So take out your box chart and have your box chart handy and try to figure out, okay, what would lithium look like? How do those electrons go? So you'd put them in the lowest level. So 1 up, 1 down in the 1s orbital. And then you have the third electron facing up in the 2s orbital. So instead of showing all the boxes and the arrows, give me a second here, you're going to show just how many electrons are in each level. So in the 1s orbital, you put 2 electrons. In the 2s orbital, you put 1 electron. Easy peasy. Let's try it again. Let's imagine 11 electrons. So 11 electrons is sodium. So take a look at sodium. If you were going to put it in the box chart, really have your box chart available to you. So you'd put 2 in the 1s, 2 in the 2s. Now we're going to go across to the 2p's. And remember, you're filling the bunk beds one at a time. That was from our POGL. So it would go 2p1, 2p2, 2p3, and then 2p4, 2p5, 2p6 upside down. So that filled the 2p6, and then we need to go one more level, and that's to the 3s1. So that last electron gets added in the 3s1. So then you just write it that way. You don't need to show any of the boxes. This is just an efficient way. Now, I know you're like, oh my gosh, this is hard and whatever. You're going to find out that there's a reason that we're doing this. This gives you a lot of information about how stable an atom is, how many electrons it wants to get rid of, or how many electrons it could gain to be stable, whether it's close to a noble gas configuration, all kinds of things. We'll get there. Okay, and let's try one. Let's try some examples that you can do on your own. So I'm going to suggest that you pause my video right now, and that you box chart these so that you know what they are. And you might be getting to the level now, if you've done the box chart enough, that you could kind of mentally. So look at your box chart. Imagine, okay, 1, 2, count your electrons. So for aluminum, you're going to need 13 electrons. So imagine 13 arrows, and how far would you go? And now I want you to write it out. 1s2, 2s2, 2p6, like that. Then go to silver. Where's silver? Silver, it's going to take me a second. Silver is number 47. Oh my goodness, 47, KJ? That's a lot. That is nothing, people. Your last one is francium. Francium is 87. Can you figure it out? In case we can't see it on our gold box chart that I give you, you would need to use a larger box chart. So let me see if I can switch tabs here for a second. Give me just a moment. I'm going to switch tabs here really quickly. I don't know how to switch tabs. I can't. Okay, well, I was going to show you that there are other box charts that go into the F levels. Your little gold box chart doesn't have all of the orbitals possible. So if you're missing some, take a look in your textbook. Your textbook has the full orbitals and everything. So see if you can do francium. Okay, pause the video. Try to do it yourself, and then restart the video when you're ready. I'll give you a second to pause me. Okay, let's move on. So for aluminum, you should have answered 1s2, 2s2, 2p6, 3s2, 3p1. That last electron should have been up in the 3p orbital. So for silver, it's going to be a lot, and it's going to be ridiculously long. Wait till we get to francium. Okay, silver, I'm just going to let you read it. I'm not going to say anything more. Here, actually, I will say one other thing. You're going to write, there's sort of some debate about the way in which we're supposed to write it, and I'm not concerned about it. So I'm going to ask you to write it in the order that the orbital gets filled. You will see sometimes, let's look at the threes and the fours here. So notice it goes 3p6 and then 4s2 and then back to 3. So some textbooks, some things online will tell you to put all the principal energy levels together. So all the big number 3. So what they're suggesting is that you write 3s2, 3p6, 3d10, and then 4s2. I don't care which way you do it. If you're happier doing it in the order that the boxes, the levels show up on your box chart, we are good to go with that. It's not important at this point. We can work out the details a little bit later. Okay, let's go to francium. Francium is ridiculously long. Let me get my image out of the way here. Did it move? Oh, I thought I could move my image and it's not moving. So anyway, that's a 7s1 at the end. So crazy long, and no scientist in their right mind is going to want to write anything that long. Nobody has time to write anything that long. So that's where the shorthand is going to come in, and we're going to learn how to do some things a little bit faster. So let's go over a few things, why we even care about electron orbitals and what it tells us. So first of all, we're going to try to define valence electrons. And I'm going to start by defining valence electrons. Generally, are those electrons in the outermost principal level of an atom. However, notice there's a little asterisk, and then down at the bottom it says valence electrons for the transition metals. Now, if you don't remember from junior high what the transition metals are, that's these metals that are in this sort of middle section here. Those are called the transition metals. So it says valence electrons for transition metals are more complicated. We'll learn about them later. Don't worry about them. So I'm going to give you the easiest scenarios. I'm never going to give you the trickiest scenarios. So valence electrons are tricky. I'm not going to give them to you. Okay, so valence electrons are in the outermost principal level, so that's the biggest number. And then the core electrons are the electrons in the inner principal levels of an atom. What? Let me see an example. Here's an example. So this is the electron orbital chart, the longhand version for sulfur. 1s2, 2s2, 2p6, 3s2, 3p4. So everything that's written in green, those are the core electrons. Those are the electrons on the inner levels. The ones that are marked in blue, notice that they have the biggest large number. So they both have a 3, 3s2, and 3p4. Those are the valence electrons. So anything that has the largest principal energy level, then that's the outermost, those are the outermost electrons, and we're going to call those the valence electrons. And again, I'm not going to give you tricky ones. I'm only going to give you ones that are fairly straightforward as we're going. Okay, so now let's try the shorthand. This is called noble gas notation, or just straight up shorthand. Noble gas notation allows us to take really difficult ones like francium and write them in just like a couple of letters and numbers instead of some giant ridiculous set of numbers and letters. So it says the configurations are written showing only those electrons that are added after the previous noble gas. Okay, let's just review really quickly what your noble gases are. So on your periodic table, the noble gases are the ones on the very, very far side. I'm backwards here. They're on the very, very far side of your periodic table. Those are the noble gases. So anything that's added after the most recent noble gas, that you're going to write down. What? Let's take a look at some examples. The previous noble gas is shown in brackets. So here's an example. Sodium, find sodium on your periodic table. So sodium on your periodic table is number 11. Number 11 is sodium. Now go back to the closest noble gas. The closest noble gas that was before sodium is number 10, which is neon. That's the noble gas that came before sodium, not after sodium, but before sodium. So it says sodium could be written 1s2, 2s2, 2p6, 3s1. However, it could also be shown as neon in brackets. That's the 1s2, 2s2, 2p6. That's 10 electrons. And then the only part you have to write is what comes after the last noble gas, which in this case was neon. So all you have to write is neon in brackets and then 3s1. Way easier. And francium will be insanely easy once you get the hang of it. Okay, so take a look. Here's chromium. Chromium is number 24. It's in the middle of the transition metals. I'm trying to point to it right there. Okay, number 24. So if you have to write it out, it's a really long one. But if we try to make it faster, go to the noble gas that comes before it. So before 24, the noble gas that came before it is argon number 18. So you write argon in brackets, AR, and then all of the electrons that came after argon. So argon had 18 electrons. So these electrons right here, 1s2, 2s2, 2p6, 3s2, 3p6, that's argon. These represent argon. And then everything beyond argon, you need to write down. Okay, so let's see if we can try some other examples. You can go ahead and pause this video at any time. It says write the noble gas notation for the following elements: sulfur, barium, and iodine. I will give you a moment to pause my video, and then I will show you the answers. Let's go. Okay, so for sulfur, the right answer would be neon in brackets, and then 3s2, 3p4. For barium, you would have xenon in brackets, and then just 6x2, 6s2. It's just 2 electrons past xenon. For iodine, you would write krypton. Krypton is the noble gas that came before it. And then you have quite a few. So you have 5s2, 4d10. Ooh, that is a big number. And 5p5. So how many electrons did it have beyond krypton? It had 17 electrons past krypton. Okay, let me know if you have any questions about that. The last thing we're going to do is just really quickly, I showed this a little bit in class, but I want to make sure you're feeling comfortable with it. The orbital shapes. We're going to expect you to know 2 types of orbital shapes, the S's and the P's. The D's and the F's are so complicated that we're never going to draw them. We're never going to expect you to know them. But the S's and the P's are pretty straightforward. So the S orbitals are a sphere around the nucleus. And I was just researching what the letters S, P, D, and F stand for. I don't even understand what they stand for, but I thought the first one stood for sphere, and I'm wrong. It doesn't stand for sphere. It's coincidence. So this tells you about the shape. The letter S tells you that this particular orbital is sphere shaped. And what's really important is the orbital, they don't go in a circle or in a sphere like this. It's the dots show you the probability that the electron will be in that particular location at any given moment. So if you notice, the dots are more sparse on the outside, and then they become more and more dense in the middle, and then they become less dense again. So what they're saying is it's a cloud, and that you're most likely to find the electrons in this dense area here. You might find the electrons out here, and my understanding is that you might find that electron across the universe. It would be extremely unlikely, but it theoretically could happen. So that's a low probability. High probability that it's going to be in this dense area in this cloud. Okay, so now the 2s orbital is really similar, but it's a level out. So it's further out, and it says it's similar to the 1s, except the electron is most likely in the region farther from the nucleus. So it's most likely in this dense region out here, but could it be right there, or could it be here, or could it be across the universe? Sorry, I shouldn't even be mentioning that. It could be. So this is the area where the electron is most likely to be found, but it does not travel in a circle the way Bohr was imagining. It is not like the solar system at all. Not that there's circles anyway, but Okay, and then the last one that you do need to know are the p orbitals. The p orbitals, we say, look like dumbbells or balloons. There's kind of one on top and one on the bottom. There are three of them for each of the dimensions in three-dimensional space. So there's one that follows the y-axis, there's one that follows the x-axis, and there's one dumbbell that follows the z-axis. So now I want you to take a look at axis. I said that funny. So now I want you to take a look. So here's the s orbital. Here are the three different p orbitals. If all of the p orbitals are full, you get this beautiful flower shape, except that it's three-dimensional. Okay, and it's going to get better. So these are the d orbitals. What? That's an orbital? What is that? It's just the probability where that electron is likely to be found. It's not that the electron is traveling like this. It's just the probability where the electron is likely to be found. And then the f orbitals are even more fun. So this is what I found when I researched what does SPD and F actually stand for. So it says the SPD and F respectively stand for sharp, I thought it was sphere, sharp, primary, diffuse, and fundamental. The letters and words refer to the visual impression left by the spectral line's fine structure that occurs because of the first relativistic corrections, particularly the spin orbital interaction. On that fun note, you don't need to know that, so don't worry about it. Students often want to know what SPDF stands for, and I didn't know what it stood for, so I thought I'd look it up for all of us. Okay, everybody, that's it. Now you're ready to move on to your assignment. Have a good day. Bye-bye.